We're going on a journey into the world of spintronics.
You mean like,
Yeah, spintronics. It might sound like sci-fi, but it's a real field with the potential to, well, to revolutionize a lot.
It really does. And it all starts with something so small,
Yeah.
the spin of an electron.
We're talking about those tiny particles, right? Like electrons, the foundation of everything.
Exactly.
We learned about them in school, mostly about their charge, how they flow, electric current. But their spin, that's different.
It is. For a long time, electronics just focused on the charge. But spin, that's an intrinsic angular momentum, a powerful force. Think of it like we've been playing the piano with only half the keys. Spintronics unlocks the rest.
Wow. Okay, so more than just on and off signals,
Yeah.
we have information coded into the spin itself.
Precisely. And that's where things get really interesting, because electrons spin, well, it's not limited to just two states.
It's not just like a traditional switch.
Right. It's not just a 0 or a 1. This is where quantum mechanics comes in. Electrons can be in a superposition of states, so they can be both spin up and spin down at the same time.
That's mind-blowing.
It is counterintuitive, but that's quantum mechanics for you. And it opens up huge possibilities for spintronics, especially for quantum computing. Imagine a computer that can calculate with a blend of both 0 and 1 at the same time.
It's not much power.
It is.
Okay, so we've got this idea of spin and its potential, but how do we actually use it, control it?
To build spintronic devices, we need what are called spin-polarized currents.
Spin-polarized currents.
Imagine electrons, all spinning in the same direction, either up or down.
How do we even make them do that?
One way is to use, well, materials that naturally align spins. We call these ferromagnets, like a refrigerator magnet.
Oh, okay.
They stick because the electron spins inside are all aligned, creating a magnetic field.
So we can use that to inject electrons with a specific spin.
That's the idea. There are other techniques too, of course, like spin filtering, where you use special materials or structures to select for electrons with a certain spin, like a filter.
Okay, so we've got the building blocks, the spin-polarized currents, but, they have to go somewhere, right?
You're right. And this is where it gets tricky. Imagine you align all the spins perfectly,
Okay.
but then they bump into things, atoms and impurities.
Oh, so they lose alignment.
Exactly. It's like, it's like a synchronized swimming team getting disruptive.
Aha, I like that.
We call this spin relaxation.
So we need materials where the spins stay aligned longer.
Right. Materials with long spin diffusion lengths, so they can travel further, without losing that spin information.
The type of material really matters.
It does.
But it's not just about keeping them aligned. It's also about how they rotate, right?
You're talking about spin precession.
Yeah, spin precession.
It's another key concept. Imagine the electrons moving through a magnetic field. Their spin axes are to rotate, like a spinning top wobbling.
Okay, I can kind of see that.
And by adjusting that magnetic field, we can control how they rotate. We can orchestrate the spins.
From tiny spinning tops to an entire orchestra.
That's the beauty of it.
So how do we translate all of this into something real?
Now we're ready to dive into some actual spintronic devices.
Okay, let's hear it.
Let's start with giant magnetoresistance, GMR.
GMR.
It's a game changer. It's why we can fit gigabytes of data in our pockets.
Okay, tell me more.
GMR uses this really fascinating thing that happens when you layer ultra-thin materials, magnetic and non-magnetic. So picture a sandwich, a layer of iron, then chromium, and then more iron.
Okay.
Depending on how those iron layers align, their magnetic fields, the resistance of the whole structure changes.
So we're controlling how easily electricity flows through it.
Exactly. It's like a valve for electrons, but controlled by the alignment of spins, not a physical barrier.
And this is what changed hard drives.
It is. GMR sensors can measure magnetic fields so precisely that we can read data on a hard drive with incredible detail. GMR was a huge leap for data storage. We went from megabytes to gigabytes to terabytes.
All because we can control these tiny spins.
It's amazing, isn't it? And that was just the start. We also have TMR.
Tunnel magnet resistance.
Yes. You remember.
You mentioned it. It's like GMR, but different, right?
Right. Instead of a metal spacer, TMR uses an insulator, so the electrons have to tunnel through.
Tunnel.
Yeah. And their ability to do that depends on their spin.
So only some get through.
Only the ones with the right spin. TMR is even more sensitive than GMR. It's like having an incredibly sensitive microphone.
Wow. And this has other uses.
Definitely. TMR is used in medical imaging, navigation systems, even MRAM, magnetic random access memory. It's faster and more energy efficient than the flash memory we use now.
Okay, so we've got these amazing sensors, but we also talked about something even crazier. Controlling magnetism with spin.
Spin transfer torque.
Yes. STT. Can you remind me how that works?
Sure, with STT we can change the magnetization of something. Not with a magnet, but with a spin current.
So we don't need a big, bulky magnet.
We don't. It's like using a stream of tiny spinning tops to knock over a bigger one.
I like these analogies. So this STT lets us manipulate things at the nanoscale.
Precisely. And it paves the way for all sorts of new devices. Smaller, faster, more efficient.
We're really entering a whole new era. It's amazing. But I know there's more.
What if we could control magnetism without any magnets at all? That's where spin-orbit coupling, or SOI, comes in.
SOI, right. The one that's kind of related to relativity.
It is. SOI comes from the interaction of spin and motion. And an electric field, it's a relativistic effect, meaning the electron speed, which is pretty fast, by the way.
Oh, yeah?
It's a significant fraction of the speed of light. That speed plays a role.
Wow.
Imagine an electron zipping around an atom's nucleus, really fast. Einstein's theory tells us that affects how it experiences space and time, and that influences how its spin interacts with the electric field.
So the spin is getting, like, twisted.
That's a good way to think about it. That twisting, that SOI, it's what lets us manipulate the spin.
And this leads to the spin Hall effect.
Yes, the spin Hall effect, is where a normal electric current can create a separation of spins.
Wait, really?
Electrons with spin up get deflected one way, spin down another. It's like sorting them.
Wow.
And there's also the inverse spin Hall effect, where a flow of spins creates a voltage.
So we can go back and forth, charge and spin currents.
We can, and this means we can build all electrical spintronic devices. No magnets needed.
So SOIs is really taking this to a whole new level.
It is.
Not just reading the spin, we're actually controlling it, creating entirely new things.
Exactly.
And what kind of new things are we talking about? It's incredible to think about all the things we can do.
It is. Spintronics moves so fast. But you're right, we're only just getting started. There are challenges too, though.
Oh, yeah. Like what? Making them smaller, getting them to work at room temperature.
Those are definitely important. But a lot of it comes down to the materials. Remember spin relaxation?
Yeah, the spin's getting scrambled.
Right. The material makes all the difference.
So we need to find the perfect material.
In a way, yes. We need materials that let those spins travel further without getting disrupted. Materials with long spin diffusion lengths. And ideally, strong spin-orbit coupling, too.
Because then we can use electric fields to control the spin?
Exactly. So materials science is a big part of spintronics.
It makes sense. But it's not just finding the right material, is it?
It's not. It's also about how they're combined. The interfaces between them.
The interfaces?
Yeah. Think of it like a highway. Even with perfect roads, if the exits are messed up, the whole trip is a mess.
Ah, okay. So the interface can scatter the spins.
It can, even if the material itself is great. So a lot of the research is about, well, it's about engineering those interfaces.
At the iconic level, right?
That's right. And when we make devices smaller,
nanoscale.
Yeah, things get even harder. Quantum effects start to really matter.
But those are good, right, for quantum computing?
They can be. But they also make things less predictable. It's like the electrons become harder to control.
I see. We need to find ways to use those quantum effects, but also manage them.
Exactly. And this is where spintronics connects to other fields, like spin caloritronics.
Spin caloritronics, what's that?
It's about spin, charge, and heat. What if we could control spin with heat?
Instead of magnets or electricity.
Right. And it turns out we can. There's something called the spin-Seebeck effect, where a temperature difference creates a spin current.
That's pretty wild, like turning waste heat into energy?
It could be. And then there's spin optics.
Spin and light?
Yes, light can control spin. And spin can influence light. It opens up a lot of possibilities. Super fast switches, sensitive detectors, even new ways to store data with light.
So spintronics is really connected to all these different areas.
It is. It's a really interdisciplinary field. Physics, materials, science, chemistry, engineering, even computer science.
Wow. It's amazing to think about. This has been incredible. But it does feel like, well, it feels like we're still at the beginning.
We are, and it's all happening so fast. What we talked about today might seem like science fiction, but it's becoming reality.
So if someone's just starting to learn about spintronics, what's the main thing they should remember?
I'd say it's this. Spintronics is more than just technology. It's a whole different way of thinking about electronics. The universe is stranger than we think. We're not just moving electrons anymore. We're controlling their spin. That's the quantum world.
And it's full of possibilities.
It is. There's so much more to discover.
Well said. Thanks for taking us on this deep dive into spintronics.
It was my pleasure. Thanks for having me.
And to everyone listening, keep exploring, keep asking questions. There's so much out there to learn.